You may have heard of an abstract data type called the dictionary. And what a dictionary does is it stores a set of items or nodes, and each node has a distinct key. So each node has a distinct key. Of course, they have to be distinct unless otherwise stated. And for some node X, so let's say for node X with key K in the set S, we have the following operations. And in order for it to be a dictionary, it must support all three of the following operations. So the first is called search. So we can search within this set for a particular key. And what if the key doesn't exist? If key K doesn't exist in the set, then we return null. Okay, so that's for searching. What about for insertion? So if we want to insert into this set S a new node, then we have to take care of duplicates. What if there's a node already in S with a key that has the same key as X? So we don't want to duplicate nodes with the same key. So in case we have the same key, then what we do is we replace the old node with this new node X. So this new node X will replace the old node that was there, and it overwrites it, and this new node becomes the only node with the key it has within this set S. So if there is a duplicate, replace it with X. And the way we define duplicates, once again, is duplicates exist if there is a node with the same key as X. And you can't see that, so let's put it there. Okay. All right, so that's for insertion. How about for deleting? So delete. So to delete something from S, so we're trying to delete something from S, we try to delete this node X from S. Well, the thing to remember is, sure, we are specifying a node to delete, but we don't even know, we don't really have a reference to that node, right? So we don't have a reference to that node, so how do we even find it within S? Well, you might ask, why don't we specify the key to search for and search for the keys? Well, if you look right here, there's already this method search that does that for us. So we want each method focused on one single task, so we don't want to make it search for a key here. That's why we don't specify, okay, we want to give it a key. We just specify giving it a sort of node, and the searching already would have happened. And remember, if you wanted to search for a key, this method is fine, perfectly fine, and it's going to do that for us. And whatever it gives us, that's what we can put in here if we really need it. So finding the reference to X is not a problem. Once we have it, we just delete X. All right, so these are the three operations that if we were to call some kind of structure an ADT, which is a dictionary, some ADT and a dictionary, then it has to support these three operations. So okay, now that we know that, let's actually talk about one data structure which implements the dictionary. So we'll move that up, go down a little bit, and now we want to talk about BSTs. Okay, so BST, or binary search tree, right? So this is what we're talking about. Okay, so the binary search tree can implement one, in one way it can implement a dictionary. So how does it implement a dictionary? Well, let's see. So BSTs have a few distinct properties. So BSTs have that nodes each possess a key, and we're going to enforce that this key be distinct for the sake of being a dictionary. And that's the first thing it needs to have. The next thing that is that any node's key k is greater or equal than the left subtree's keys, or in other words, it's greater or equal than any key in the left subtree. Okay, and we can pretty much copy this ditto. Right, so we can copy this, and we can say that this is lesser or equal than any key in the right subtree. Okay, so any node's key is greater or equal than any key in the left subtree, and lesser or equal than any key in the right subtree. And in fact, this thing right here, we're going to call this second bullet point. This second bullet point, we're going to call it the BST property. So we know the max heap property. Now we know also about this BST property. Okay, so this is the BST property. Now, each BST node stores the following, right? It stores, first of all, it stores the key, it stores the left child, which is a reference to a node, another node, or null. And similarly, it also stores the right child, which is a reference to another node or null. So one more thing we want to also store is the parent node. So a reference to the parent node. So we also store the parent node. Okay, so we want to store these 4 things in for each BST node. Okay, and we want to support the following operations. So obviously we'll have to support the operations for a dictionary, because after all, this data structure is going to implement a dictionary. But in addition to that, we'll also have a couple extra operations we'll support. So first of all, let's talk about the read-only operations. Right? So the read-only operations that we'll support are searching a key in the tree, which is going to be O of H, where H is the height of the tree. And hopefully that's pretty clear, right? If we have some kind of tree that keeps going to the right like that, it's pretty clear to see that it's going to be a long chain of just going to the right, to the right, to the right. Or it could be perfectly balanced and, could be like this. But in the worst case, we'll assume that we are maximizing our runtime. So we are going to find a key in the very last spot. And in the very last spot, well, what is that? Well, it's precisely O of the height of the tree. That's how many times we would have had to go to the right or left, right? It's precisely the number of times. The number of times is precisely the height of the tree. The number of times that we go right or left to find that element we're looking for. Okay, so hopefully that's pretty reasonable. Okay, so what other operation do we want to support? Well, we can get the min or max. So get the minimum or maximum node, and we just go to the right or go to the left a bunch of times, and until we hit null, we just see what node we were at. So that'll precisely be the minimum or maximum. So that's not very difficult. What about getting the successor? Or the predecessor? Well, to get the successor or predecessor, let me move everything up for a minute. So we're trying to get the successor or predecessor. So what do we see? Well, in order to get the successor, which is defined as the, okay, first let's talk about the successor. Defined as being the node with the smallest key larger than the given node's key. So say we're given the, we're given the node x, right? So this node is called x, and we have two cases. We have a case where, case 1, where x has a right child, in which case we take the minimum of the right subtree. So if we take the minimum of the right subtree, that is going to be the successor. Okay, so that's the case there. What if we have case 2 where x has no right child? So if this is the case, if x doesn't have a right child, then the lowest ancestor whose left subtree contains x is the successor. You guys can't see that, so let me actually move this. Okay, so the lowest ancestor whose left subtree contains x is the successor. So if you want a picture, how does that look? Well, so what are we saying? Let's say x, we have something like this, where, okay, this is coming from some other node up here, but this is x. That is x. And x doesn't have a right child. So it doesn't have a right child. So the lowest ancestor whose left subtree contains x is the successor. So say we have a y here. This is the lowest, this y is the lowest ancestor of this node x, whose left subtree, right? So this y is the lowest ancestor whose left subtree contains x, right? Whose left subtree contains x. So this y is precisely the successor of x, and that y is going to be the thing which is the the node with the smallest key, which is also larger than x is. Okay, so hopefully you can see that. What if it was over here? What if y was over here? Well then, now you'd have to search up the ancestors of this node y until you find that x is indeed in the left subtree rather than the right subtree of some ancestor. And as soon as you find that, that's when you found your successor. And that ancestor which has x in its left subtree first is going to be defined as the successor of x. Okay, and what about for predecessor? And what about for predecessor? So for predecessor, for the predecessor, you follow same thing as for the successor, right? Hopefully it's not too unclear. You have two cases for the predecessor. You have something which has the left child. So left child exists. Then if left child exists, then you just take the maximum of the left subtree of the left child, or rather maximum of the left subtree of x, and that is going to be your predecessor. And of course, predecessor is defined as the opposite of successor, which is the node with the smallest key, largest key lesser than the given nodes. So the largest key that's lesser than x is going to be given by taking the left child or the left subtree of x and getting the maximum of that left subtree, and that is going to be the predecessor. And if that's not there, so if x does not have a left child, then what you do is sort of case 2, where you go and find the lowest ancestor, yeah, so you find the lowest ancestor with that has the right subtree containing x. So with right subtree containing x, right? I know that's very messy, but hopefully you just heard what I said, and if you just kind of remember it as being the opposite of successor, hopefully that puts things into perspective. So successor and predecessor are both O of H operations, right? So they take the same amount of time as the height of the tree in the worst case, or rather we should say they're upper bounded by the number of steps is the same as the height of the tree in the worst case, or to the order of the height of the tree in the worst case. Okay, so we sort of understand that much. So what's left? Well, we still have to go through the non-read-only sort of operations. So the read-only operations we discussed were getting the min-max or searching through the BST or getting the successor or predecessor. But now we want to talk about the non-read-only operations, or rather mutating operations, right? So one of these is insert. So inserting a new node, which takes O of H time, right? So at the worst case, this is O of H. And this is hopefully pretty straightforward. We just traverse through the tree, right? We have some kind of tree, and we traverse through it. Okay, so we look here, oh, we want to insert to the left, so we look here, oh, we want to insert to the right. Okay, now boom, we insert something here. There, that's how we insert. So it's O of H, right? Depending on what you're inserting, kind of, you can see why it's O of H, because you need to go down at most the height of the whole tree to insert. So this kind of already gives you an intuition that a lot of things rely on the height of the tree, a lot of these operations. So hopefully we have that the height is pretty minimal, right? So, or in other words, the tree is pretty balanced and all the levels are hopefully filled as much as possible. And in fact, we'll see in the next video that there's a special kind of tree that helps us do that, that pretty much balances itself. Unfortunately, BSTs don't have that, so at the worst case, this could take O of n, where n is the number of nodes, that the tree has. So with a regular BST, we're not guaranteed, that kind of optimal insertion or search or all this performance, but there are trees out there that we can use to do that. Again, that's the next video. We won't talk about it now. Right now, what we want to talk about though is also deleting a node. So the final thing we have left to do to make sure that this is in fact an implementation, a valid implementation for a dictionary, is how do we delete nodes? Okay, so deleting nodes is the only part that remains now. And this is in fact one of the tricky parts that we need to consider. So deleting is one of the tricky parts we need to consider because we have three cases. Case one, we have 0 children, or rather we should say X has no children, and in this case we simply delete X, right? Now case 2, X has 1 child. Then if this is the case, we promote X's child, or rather X's child's subtree to the spot where X was. So the deleted node's spot is taken over by the child and its whole subtree, right? So that's that. Now what about what if X has 2 children? So this is sort of the tricky part. We need to, well, I say it's tricky, but it's actually not that tricky. It's just, we just have to consider 3 scenarios. Each of the scenarios, though, I would say is relatively simple, and you'll see even this last one. So we just replace the deleted node with the minimum of the right child's subtree. So to show you why that is, so to show you why that is the case, let's say we have this tree. Okay, so we have this sort of tree, and we want to delete this node, right? So this is the node we want to delete, and we kind of want to get rid of it. So now what do? Well, in order to replace that, what do we take? Well, according to this, it says that we replace the deleted node with the minimum of the right child's subtree. So this is the right child, and let's say it also had a left child here. So this is going to be the minimum in the right child subtree, and we take this, we delete this here, and we put it here. And now this thing is replaced by this. So now this is gone from here, gone. So it's gone from there, and now it's over here. Okay, so now we have some kind of tree that looks like this. 1, 2. Okay, so this is the new tree. And in this new tree, we see that because we replaced the old thing that we were deleting with the minimum in the right subchild, we cannot possibly have the case where this subchild is, violating the BST property, because it is certainly greater than anything in the left subchild, and certainly less than or equal to anything in the right subchild. So yeah, it certainly retains the BST property. So this is what we do. So we talked about in this video one valid implementation of the dictionary, but we see that we have O of H across the board. Even deleting, this is O of H, right? So this is, let me even state that, O of H. So deleting is also O of H, it turns out. So we have a bunch of operations we discussed. Turns out most of them are O of H for BSTs. So we can certainly, or we certainly want that H to be as minimal as possible, right? So we want the H to be as minimal as possible so that we don't have a worst case scenario where we have some linear time kind of operation where it's just a chain of all these nodes to the right or all these nodes to the left, and depending on insertion order, it's not necessarily like that, but still we could have some kind of zigzag kind of nodes, right? Anyway, my point is we have some really bad looking shapes if we don't have a balanced binary search tree. So in the next video, as promised, we'll talk about how to make sure that our binary search trees are balanced, or rather how they balance themselves. So stay tuned for that.